G'day, I'm Dr. Kev, and in this video we'll be simulating a car during acceleration. We'll use the dimensions and masses of a car, along with things like the power and gearing, to determine how the car accelerates, and then how that acceleration is affected by things like drag. Welcome to Car Design Workshop. Before starting the simulation of acceleration, we're going to need to gather a bunch of information about the vehicle. This will include things like the torque curve, the gearing, car dimensions, the weight of the vehicle and the center of gravity location, as well as some of the aerodynamic parameters. For the purpose of this video, we'll be simulating a Series 1 Lotus Elise that will act as a benchmark moving forwards. Information about this car can be gained through a number of websites, including digging into forums for more detailed information. It's not always easy to find this sort of information, and as we move on through the project, this is something that you would edit and put in better information as you find it, especially when you start to test the vehicle. Now, if we're looking at acceleration, one of the obvious things we're going to want is a torque curve. Once we have a torque curve, we'll also have the power curve. If we are not able to find a really accurate torque or power curve for the vehicle, we can use the peak power and the peak torque at the given RPMs that they're published at and construct a simpler torque curve to put in the simulation. It'll usually be accurate enough for this conceptual stage of design. We'll also need the gear ratios for the car, and these are usually easy to find on specification websites. You'll see we start with a fairly high ratio for first gear, and then often that fifth gear or final gear of a vehicle is really a cruising gear and has a much lower ratio. With this, we'll need the final drive ratio as well, and the final drive ends up being one of those things for a lot of cars that you can change independent of the gearbox and enables the whole gear chart to either increase the rate of acceleration or decrease the rate as desired. We're also going to want to put in a drivetrain efficiency number. Now, this is much harder to find without doing physical testing. You can normally assume something in the range of about 90% drivetrain efficiency, but this can be affected by things like the type of tires you're using, the type of gearboxes, and the type of drivetrain. Also related to the gear ratios is the wheel diameter of the driven wheels. We'll want this as a rolling diameter or a rolling radius that takes into account of the deflection of the wheel due to vertical load. Once we have this information, we can create a relationship that links the speed of the car to the RPM. And this is seen in this equation, where the speed of the vehicle is equal to the RPM, and we do a conversion factor to convert it from RPM to radians per second, multiplied by the rolling radius, all divided by the final drive times whatever gear ratio you're in at the given time. Now, if we take that equation and plot that for each of the gears, we can create a gear chart. And this gear chart's a fairly useful thing in of itself. We can see what sort of speeds we're likely to be doing our gear changes, and when we change from one gear to another, what RPM we'll be changing from and to. For example, from this gear chart, we can see that the 0 to 100 km/h acceleration event will only require the first two gears. We can also see from this gear chart that if the car was mechanically limited, so gearbox limited, it should have a top speed of well over 250 km/h. Now, this is not actually going to occur, as we'll see later, and really shows how that final gear, that fifth gear, is much more of a cruising gear. Now, another important piece of information we're going to need is the mass of the vehicle, or the weight of the vehicle. And we're also going to want to know where that center of gravity is, how far it is from the rear axle, and also how high it is. If we have that fore-aft location of the center of gravity, we can determine the initial vertical loads on the tires. For a Lotus Elise, the rear weight distribution is about 62%, and that means the vertical load on the rear tire will be considerably higher than that of the front. Now, the friction of the tyre is going to be determined by a coefficient of friction and the vertical load. The more vertical load we have on a tyre, the more force it can generate. Now at this point, we're only going to be using a very simple friction model, just a number for tyre friction. We won't be implementing a slip model for the tyres, and we won't be looking at how the coefficient of friction of a tyre also decreases as the vertical load is applied. For lightweight cars, that variation in friction due to vertical load is usually quite small for the range of vertical loads we're going to be seeing in this acceleration event. Now we'll see, as the traction force for the tyre is applied at a distance to the center of gravity, it creates a moment. And that moment will be resisted by a change in vertical loads on the front and rear tyres. Now we'll normally call this weight transfer. It is a reaction load though. There isn't any weight actually moving backwards or forwards in the vehicle. It's just a change in that vertical load. And that weight transfer is proportional to the center of gravity height times the amount of acceleration we have divided by the wheelbase of the car, or the distance between the front and rear tyre. And while we're talking about forces that are applied to the vehicle, we may also want to consider our aerodynamic forces. As the car is moving through the air, there will be a higher pressure on the front of the car and a lower pressure on the rear of the car. And this will cause drag, or a drag force on the vehicle. If we have a higher pressure on the upper side of the vehicle and a lower pressure on the underside of the vehicle, we can also have downforce. So we'll be applying this drag as a force, and we'll just, for simplicity in this simulation, we'll have it going through the center of gravity of the vehicle. And the equation for drag is a half rho, and rho is the air density. So at normal sea level, that would be 1.22 kilograms per meter cubed, times the coefficient of drag, times a reference frontal area, times the velocity squared. The downforce has a very similar equation, so a half rho, but instead of a coefficient of drag, it'll have a coefficient of lift times the area times velocity squared. Now, of the information that we would want from a vehicle, it's often very difficult to find a drag and downforce number. We might be able to find a coefficient, but not the frontal area, and this sort of data is not readily shared by manufacturers. When it comes to designing the vehicle in this video series, we'll be doing some CFD on these vehicles. CFD is a computational fluid dynamics, and you can see the images that I've used here is a really quick CFD study that I did in SolidWorks using a readily available model of a Cobra. Now, once we have this information, we're ready to create an algorithm or a program in order to calculate how quickly a car is going to accelerate and what sort of top speed we can expect. So this sits inside a while loop or a for loop where we just keep iterating this process until a certain condition is met. And for the purpose of this simulation, I just simulated the car for about 60 seconds of motion. So each step, I would calculate the RPM based on the vehicle speed. Once we have that RPM, we would use that to get the engine torque just from the information we had before. Once we have the engine torque, using the gearing and dimensions, we would calculate the thrust that is coming from the engine. Because we have the vehicle speed, at this point we're going to calculate both the drag and downforce. Once we've got the downforce and the center of gravity location, as well as the expected longitudinal acceleration, we can calculate the load on the driven wheels. From this load, we can multiply it with our friction and we can get tire grip. Once we have both the engine thrust and the available tire grip, the traction force of the vehicle will be the minimum of the engine thrust or the tire grip. Once we have that traction force, we just subtract the drag force from that and divide it by the mass, and we have the acceleration in the forwards direction. And then there's a simple step where we say the new velocity will be the original velocity of the car plus this acceleration times a delta t step or a dt step. And then the displacement or the distance traveled will be the current displacement of the vehicle plus the velocity times that same dt or delta t step. Now the delta t you use can be used to effectively design the resolution of your simulation. If you make the delta t too large, the simulation will be too inaccurate, and if you make it too small, it can take a long time to run. So for the purposes of this simulation, I set it at 0.005 seconds, which means that's the absolute limit of accuracy of the time that I'm going to get, but there's actually quite a few other things that are affecting the accuracy already. Now at the launch, at the very beginning of the acceleration, we'll hold a fixed launch RPM until the vehicle's driven wheels RPM will match that particular speed. This is simulating a perfect launch where either the driver is releasing the clutch at the absolute perfect rate or modulating the throttle. Now as we're doing this loop over and over again, we do need to check for when we have a gear change. So this is just an if statement that sits nested in this loop, that if the RPM is greater than a change RPM and the vehicle is not already in the top gear, then a gear change is initiated. Now if a gear change is initiated, we have a variable that is the time since the last gear change, and that's reset to 0. And until that time is greater than a set time we allow for the gear change, we set the engine torque to 0. Obviously, this is a fairly simple and harsh clutch model, but it works reasonably well for this sort of simulation. So if we were to do this for the Lotus Elise Series 1, these are the sorts of results we would expect. We can see here, this is the velocity versus time. We can clearly see gear changes occurring, and you'll notice that in those gear changes the velocity will decrease slightly during the gear changes, and the amount of decrease will increase as the car's going faster. So as we're doing the gear change, the power comes off, but the drag is still there, slowing the car down. We can also see from this graph that the 0 to 100 time is about 5.5 seconds. And we can see how much the car slows down its acceleration over time. We can also plot the distance versus time, and that'll help us determine how long it takes to travel a certain amount of distance. For example, if we wanted to know how long does it take this car to do a quarter mile. The other obvious result to look at would be acceleration versus time. And we see in the early stages of acceleration where we're using every last little bit of the tyre grip that we can, the acceleration is reasonably high. As we go into a gear change, the acceleration drops. We'll actually see some negative acceleration. And then as we're going into the power region where we're using the engine, the acceleration keeps dropping off as we're going faster and faster. This can clearly be seen when we look at the acceleration versus velocity, and we see a marked drop off of acceleration as the speed goes up. Now, a really good way to look at this acceleration and how this is behaving is to create a traction curve. So the way we create a traction curve is to really plot 3 lines. One will be the tractive force from the engine, one will be the available tyre grip, and one will be the drag force. The tractive force that we'll be using to accelerate the car will be the minimum of that tyre grip or the force coming from the engine, and the amount accelerating the vehicle will be the difference between that tractive force and the drag force. Now in the lower speed regions of this graph, we see that the torque available from the engine, the force available from the engine, is greater than our available tyre grip. And this shaded region shows us where the car's acceleration is going to be traction limited. Once we're out of this shaded region, the acceleration of the car is limited by the torque from the engine. Now, before going on and making any design decisions using these simulations, it's worth considering some of the limitations that we've introduced with this method. The first is that we're assuming a perfect driver. So perfect use of clutch, perfect use of throttle. We're also not including the angular acceleration of the rotating masses, such as the wheels and tyres. Although in practice, this rotational mass can be included in a model like this just by applying a factor to the vehicle mass. We have a simple tyre model. We're not including load-dependent friction, and we're not using a slip model for the tyre. Now this is something that can be somewhat accounted for by using a slightly lower than expected friction coefficient. And this is something I used existing test data in order to sort of calibrate this simulation based on real life performance of a Lotus Elise. We're also not including any suspension in the vehicle. There will be things like slight vertical movements of the center of gravity. There are definitely damper effects, so we can see that the load on a tire in an event like this isn't going to be constant. There's going to be a fair amount of variation. And we're also not including anything like anti-squat, which will use the angles of the suspension arms in order to alter the vertical loads on the driven wheels. Now this sounds like quite a lot of error, but that's okay because there are actually much larger sources of error than these that we're already having to deal with. So we don't really know what the drivetrain efficiency is. We don't know what the coefficient of the friction of the tyres is. And in fact, even if we had good tyre test data, that coefficient of friction would be different for different surfaces. So we could really only do that test on the surface we're expecting to run on and do the calculations based on that. We also, for the design of the vehicle, at the early conceptual stage, don't even know the expected weight and weight distribution of the car. So that means that this simulation isn't going to provide a super accurate result. Now we can make this more accurate as we gather more information along the way, or much more likely, we can use something like this early on, and then when we're developing the vehicles, we do physical testing. But what a model like this is really good for is having a look at the fundamental sensitivities during a conceptual design phase when we're making the big decisions. This is the traction model from the Lotus Elise as it is. Now the time 0 to 100 of this vehicle is about 5.5 seconds. And we can do some really different things here. So we could take this rear-wheel drive Lotus Elise and turn it into an all-wheel drive car. Now if we were in an all-wheel drive car, the amount of force available from the tires is greatly increased. In fact, it's more than the torque of the engine at all regions. Now this would actually be quite difficult to drive. You would be needing to let the clutch out over that whole first 0 to 50 kilometers an hour region. But if you manage to do that, the time comes down from about a 5.5 second run to about 4.9 seconds from the 0 to 100. We can also have a look at what happens if we run the Lotus Elise as a front-wheel drive car. Now here, the weight transfer, or this change in that vertical load on the driven wheels, works against us. So the more the car accelerates, the less traction there is on the front tires. And we can see that the region of traction limits is much larger for a front-wheel drive car than it is for the rear-wheel drive car. And our time goes from a 5.5 second run to a 6.8 seconds 0 to 100. You'll actually notice that the available grip from the tires increases as the speed goes up, and that's just because as the acceleration of the vehicle is lowering, there's more load that stays on the front tires. This is a fairly obvious reason why we wouldn't want a front-wheel drive car in this case. Now these simulations, they're somewhat platform indifferent. You can create a simulation like this in Excel. In fact, most of the time I do create these simulations in Excel. They're fairly easy to create. They're fairly messy looking, but they get the job done. But for this video, I put this into MATLAB, and this allows me to do sweeps of parameters fairly easily to be able to analyze the sensitivity of the time to different parameters. Now, first and really obvious one is, how does the acceleration of this car change as we alter the mass? So here we see the mass changing from 500 to 1,000 kilograms. And you'll notice for much of that region, there's a fairly linear decrease in time until we start to drop below about 575 kilograms. Once the mass gets low enough, then that whole 0 to 100 kilometers an hour ends up being traction limited. So any reduction of mass after that point doesn't help the acceleration at all. If we wanted to improve the acceleration with this lower mass, we would need to have a grippier tire in order to increase our traction limit. Now, some of that will be dealt with if we included some load dependency on our coefficient of friction, but we would still see this tapering off, or this lowering of this gradient, as we get to the lower masses. A similar thing happens with power. So I applied a power factor here where I could increase or decrease the power just as a scalar, not putting a different engine in. And if we drop to say 50% of the power, our 0 to 100 kilometer an hour time greatly increases, almost doubles. But as we go up in power, there reaches a point where there's basically no improvement. And this is because we are just traction limited again, just like with the mass. So this is indicating that there are practical limits to the sort of mass and power we might want in this vehicle. Now, I am really just looking at acceleration here. The big advantage of power comes if you want to increase your top speed. So considerably more power means a considerably higher top speed. So I put another factor in the simulation, which we can call a grip factor. And this is just multiplying the coefficient of friction by a percentage. And we can see a relatively consistent improvement in increasing grip. Now, it will tail off a little bit because as the grip goes up, then we're spending more time in the power limited region of that traction model. So it looks like grip is a really good way to increase our acceleration from 0 to 100. One of the ways we can do this is by moving our center of gravity more rearwards in the vehicle. Now, a Lotus Elise is already got a fair amount of weight over the rear axle, about as much as you could expect to put in a car that we might be designing. In fact, I'd probably expect that for Project 171, we would see a slightly lower amount of weight on the rear as compared to the Lotus Elise. And you can see here that as we reach a point where there's a lot less traction, so if we're going to about 47% on the rear, we see a marked increase in the gradient of this curve. Now, another way we might want to think about increasing the grip to reduce the traction limited region would be to apply some downforce. And here I've changed the downforce from having a lift of negative 0.2 on CLA to about 0.5 on CLA. And you'll notice that there isn't much change in that 0 to 100 time. And the main reason for this is that downforce is a velocity squared term. So if we're looking for a lot of force down in that 0 to 100 kilometers an hour region, we're just not going to see it from our aerodynamics. And why it doesn't help us in downforce, it means the drag doesn't actually hurt this time too much either. So I applied a drag factor here where I could halve the amount of drag on the car or double the amount of drag on the car. And we can see that even with quite a large amount of change to the coefficient of drag, we don't see a lot of change to that acceleration time. So this indicates that we're probably not going to have to worry too much about making this car particularly streamlined or particularly low drag if we're really mainly focused on acceleration 0 to 100 times. Another factor we can explore is the gear change time. And this is either getting into how well the driver changes the gears, or if we were to install something like a paddle shifter. And it turns out just about every 0.1 of a second you're able to take out of that gear change time ends up improving your 0 to 100 time by about the same, by about 0.1 of a second. Now, this means it's probably easier to improve your 0 to 100 time by changing your gear shift system and how you're using that, rather than trying to make a marked improvement to the drag coefficient of the car. And the last sensitivity I want to have a look at is, say, this acceleration versus the final drive. And here we see a fairly moderate change here. As the final drive is increasing, we're generally decreasing the amount of time, but then there is a sudden jump in this graph. And what's happening here is we're crossing over from using just the first 2 gears to using the first 3 gears in that 0 to 100 kilometers an hour. And by having that extra gear change in there, we have basically that gear change time added to our 0 to 100 time. In fact, unsurprisingly, it looks like the Lotus Elise is a really good balance of mass and power and final drive in order to produce quite a good 0 to 100 time for the vehicle. Now, another way that we might want to look at this is see all of these parameters on one chart. And we could do a sensitivity analysis here where we look at plus or minus 10% on each of these values. And here I've ordered them in order of importance. So the most important one for producing time is grip, then the center of gravity location, then the power, then the mass of the vehicle. And we'll notice that the gear change and the drag are so much smaller influences on the overall 0 to 100 time. Now, just because the grip and the center of gravity might be more influential on the time, it doesn't mean that they're easier to change. So changing your center of gravity location by 10% is most likely considerably harder than changing your power by 10%. And the fact that some things are easier to improve, such as power, is going to indicate what we saw in a previous video where we saw that the power to weight of vehicles continue to increase over the years, but mainly on the back of increasing power rather than decreasing mass. It's just more cost effective that way. Now, there's a few other things we can do with a simulation here, and we are going to be using this tool to help us with the next phase of our project, which will be our engine selection. So I hope this has been an enjoyable video for you to watch, and I look forward to taking the next steps in future videos. Thank you for your time.